Hi everyone, I want to show you two different methods in which we can prove this series. The first one we'll do it by producing a telescoping series, and in the second one we'll use complex forms. So looking at the first method first, what we can do is we can times s by 2 sine x over 2. So that we can write 2 sine x over 2 cos x plus 2 sine x over 2 cos 2x, and upwards until we get to 2 sine x over 2 cos nx. Because now we can use the identity for 2 sine a cos b, which will equal sine a minus b plus sine a add b. And so we can apply this identity to each of our terms in our series. So now the first term we can write as sine negative x over 2 plus sine 3x over 2. The next term will become sine negative 3x over 2 plus sine 5x over 2. And we'll continue upwards until the very last term will become sine 1 minus 2n over 2x plus sine 2n plus 1 over 2x. And what you might notice now is that sine of negative 3x over 2 is negative sine 3x over 2, so these two terms are going to cancel out. Likewise, sine 5x over 2 will cancel out with another sine x over 2, and all of these terms in the middle are going to cancel out with each other, leaving us only with the first term and the last term. So this all becomes the following. And now by replacing sine of negative x over 2 with minus sine x over 2, we can write this in the following way. And once more, to simplify the right side, we'll use the same identity we used earlier. So sine of a minus sine of b can be written as 2 sine a minus b over 2 times cos a plus b over 2. And so when we sub in our terms a and b, we end up with the following equation. And so finally, dividing through by 2 sine x over 2 will give us the final result. Now for the second method, we can take advantage of Euler's identity. So we can write S to be the sum from k equals 1 to n of e to the I kx. But given that we're only interested in cos kx, then we're only considering the real part of this series. And so what we'll notice now is that this can be written as a geometric series, where our common ratio is just e to the ix. And recall, the sum up to n of a geometric series is a times r to the n minus 1 over r minus 1, where a will be our first term and r will be our common ratio. And so we can write our series S to be the real part of e to the ix, since that's our term a, multiplied by e to the ixn, since that will be r to the n, minus 1 all over e to the ix minus 1. And what we'll do now is we'll use a nice little trick on this part here to simplify this to be in a nicer form. And we can do that by taking out a factor of e to the ixn over 2 in the numerator. And we'll take out a factor of e to the ix over 2 from the denominator. And the reason why we want to do this is because now we can write each of these parts in terms of sine. So this comes from the fact that e to the I k theta is cos k theta plus I sin k theta, and e to the minus I k theta is cos k theta minus I sin k theta. And so when we minus these two equations from each other, we have e to the I k theta minus e to the minus I k theta is equal to 2I sin k theta. And now notice the similarity between this form and these two forms over here. And so when we sub this in, replacing k, we end up with s equaling the real part of e to the ix times e to the inx over 2 over e to the ix over 2. And then writing these parts in terms of sine, this will become 2I sine nx over 2 over 2I sine x over 2. And so these two i's cancel. Simplifying all of this, we can write this as e to the I n plus 1 over 2x, and then being multiplied by sine n x over 2 over sine x over 2, and then not forgetting to be taking the real part of everything. And then now, given that we're just taking the real part, this bit here can just be written as cos n plus 1 over 2x, and then multiplied by sine nx over 2 over sine x over 2. And so we're done.